we'll wind up the class with a few closing remarks on gravitation required for this level. First things first, let me give you a very quick incomplete crasher on what an ellipse is, right? Because that would be relevant to some of the final closing remarks on gravitation. Okay. Now, if there are two fixed points, S1 and S2, if there are two fixed points, S1 and S2, and if P be a moving point, and P be a moving point such that PS1 plus PS2 is a constant, that constant is commonly referred to as 2A. Sum of its distances from two fixed points is a constant, PS1 plus PS2 is a constant. Then the path that P describes is referred to as an ellipse. The path that P describes is an ellipse. All points P lying in the plane of S1 and S2 such that the sum of the distances from S1 and S2 is a constant equal to 2A is an ellipse, The path that P is going to describe is an ellipse. Now, in our scheme of things, to describe the path of P, if we choose the coordinates, variable coordinates x and y of this moving point, variable coordinates x and y of this moving point, with the midpoint of S1 and S2 as O. O is the midpoint of S1, S2. O is the midpoint of S1, S2. And the line passing through O, S1 and S2 as the x-axis, perpendicular to the x-axis passing through O as the y-axis. Then the relationship between the x and the y coordinates of this moving point at any juncture is going to be x squared by a squared plus y squared by b squared equal to 1. X squared by a squared plus y squared by b squared equal to 1 would be the relationship between the x and the y coordinates of this moving point, where a and b are constants, for the ellipse. Now, what are these constants? Now, like I said, it'll be an incomplete crasher, but nevertheless, good enough at least for the requirements for gravitation. The ellipse obtained, y-axis, this is the x-axis, this is the origin O. The two extremities on the x-axis are, A0 and minus A0, where that S1P plus S2P was 2A. S1P plus S2P was 2A. And the extremities in the y direction are 0b and 0 comma minus b. That means the path that P describes, x and y, given by x squared by a squared plus y squared by b squared equal to 1. The path that P describes, x squared by a squared plus y squared by b squared equal to 1, is bounded along the x-axis by points minus a0 plus a0, and in the y direction by points 0 comma b and 0 comma minus b. The two fixed points S1 and S2, which are fundamental traits of this entity, are called the foci of the ellipse. S1 and S2 are the foci of the ellipse. S1 and S2 are the two foci of the ellipse. And the sum of the distances of P from S1 and S2 will always be a constant and will be equal to this length which is 2a. This length is AA prime, let's say. AA prime is 2a, as you can see. AA prime is 2a. Again, in the y direction, the extremities are BB prime. Then, as you can easily see, the BB prime is 2b. The BB prime is 2b. 2a is called the major, the length 2a is called the length of the major axis, or simply the major axis of the ellipse. 2a, the distance across the extremities, A and A prime, that's 2a, that's called the major axis. And this 2b is called the minor axis. Small a is called the semi-major axis. Small b is called the semi-minor axis. Small a is called the semi-major axis. Small b is called the semi-minor axis. The ellipse is characterized by a relationship between this A and B. This ellipse is characterized by a relationship connecting small a, the semi-major axis, and small b, the semi-minor axis, given by b squared is a squared into 1 minus e squared. B squared is a squared into 1 minus e squared, where e is called the eccentricity of the ellipse. E is called the eccentricity of the ellipse. And it's a number that would lie between 0 and 1. E is a number lying between 0 and 1 and is called the eccentricity of the ellipse. The relationship connecting the semi-major axis B and the, semi-minor axis B and the semi-major axis is given by B squared is A squared into 1 minus E squared, where E is called the eccentricity of the conic section ellipse. It lies between 0 and 1. For a circle is really a special case of an ellipse. The eccentricity becomes 0. E is 0. When E becomes 0, B becomes equal to A. And when B becomes equal to A, this becomes a circle. So a circle is a special case of an ellipse with the semi-major axis and the semi-minor axis stagnating into 1. Right? Now, it can be shown this is the standard equation of an ellipse. This is a standard equation on an ellipse whose major axis lies along the x-axis, whose minor axis lies along the y-axis. And the major and the minor axis will always be perpendicular to each other, and they intersect at a point which is the midpoint of the line joining the two foci, right? Now it can be shown for a standard ellipse, whose equation is x squared by a squared plus y squared by b squared equal to 1. A and b are the semi-major and the semi-minor axis connected by their eccentricity. It can be shown that the coordinates of the two foci S1 and S2 be following. If O is the origin of coordinates, the midpoint of S1 and S2, then S2 has coordinates AE, 0. S2 has coordinates AE, 0. S1 has coordinates minus AE, 0. These are the coordinates of S1 and S2. Clear? Very clearly then, AA prime. OA prime is small a. OA prime is small a. Realize that? OA prime is small a. So S2A is A minus AE, is A minus AE. Similarly, S1A will also be A minus AE. This length is going to be A into 1 minus E, and so on and so forth, right? Now, one more fact which I just want to mention to you in connection with the ellipse. In fact, either the ellipse is defined from two fixed points S1 and S2, such that the sum of the distances from S1 and S2 is a constant and is equal to the major axis 2A of the ellipse. Sometimes the ellipse is also defined a little differently, in which case we define the ellipse as the locus of a point. If a point P moves in a manner that its ratio of its distance from a fixed point S to a fixed line L, S is a fixed point and L is a fixed line, and if P moves in a manner that SP by PM is a constant, SP by PM is a constant, which is referred to as E, the eccentricity of the ellipse, which is referred to as E, the eccentricity of the ellipse, then the path that P describes is an ellipse. The path that P describes is an ellipse. This fixed point is a focus, and this fixed line is called the directrix of the ellipse. It's called the directrix of the ellipse. So for a focus, the ellipse will have a directrix, If there are two foci of an ellipse, then it will have obviously two directrices. For each focus, there would be a corresponding directrix, which means if this is the standard equation of an ellipse, which is like a x square by a squared plus y squared by b squared equal to 1. This is one focus S, this is another focus S prime. This focus has coordinates AE0, this is origin, this is minus AE0. Corresponding to this focus, there is a directrix L, and this directrix has an equation x equal to a by e. It will be parallel to the minor axis. The directrix will be parallel to the minor axis. This is the minor axis. X equal to a by e would be the equation of the directrix. For this focus, this would be the directrix, and its equation is going to be x equal to minus a by e would be the directrix of corresponding to this focus. So, in general, these are the two directrices. These are the two foci. We have a semi-major axis, a semi-minor axis, and the semi-major and the semi-minor axis related by b squared equal to a squared into 1 minus e squared. Clear? So this was like a quick crasher on ellipses, right? So we have fundamental to an ellipse, the semi-major axis, the semi-minor axis, and therefore also the eccentricity. If b and a are known, then E is uniquely established for the ellipse. Clear? It's a bounded curve and it enjoys symmetry about the x-axis as well as about the y-axis. Right? So that in a nutshell, good enough for some understanding required in gravitation, but not even close to being good for a proper discussion on ellipses in coordinate geometry, right? Now, few things. If there is a point O, a certain fixed point O, and there is a particle P whose mass is m, and there is a particle P whose mass is m. and whose distance from O is r, then the moment of inertia of this mass about O, is mr square, right? Sigma mi ri square. So in this case, just one mass. So its moment of inertia about O is going to be mr squared. That's one thing. Two, if at any point, let's say this mass has a velocity v, in a direction shown. Then there is an angular momentum. The mass has a linear momentum, which is, this mass has a linear momentum p, which is m into v. This mass has a linear momentum, which is m into v. This is the direction of the velocity, is the same as the direction of the linear momentum. And this is the line of action of the velocity. We say this is the line of action of the velocity or line of action of the linear momentum, right? From this line of action of the velocity, if you drop a perpendicular from O onto this line of action, which is D. If you drop a perpendicular from O onto this line of action, which is D. D is the perpendicular distance from this line of action V with respect to this point, fixed point O. D is this distance of V, line of action of V, the vector V, from the fixed point O. Then we have another entity defined. In addition to having a linear momentum, we have what's called an angular momentum about O. We have an angular momentum about O. Which would be mv into d, mv into perpendicular distance of the line of action of the velocity from the fixed point O. That's mv into d, mv into d. Linear momentum into the perpendicular distance of this line of action d, right? So if this angle was theta, this angle is theta, and if this r is known, then very clearly d would be r sine theta. D would be, in this case, r sine theta, where r is the radial distance of the point P, of the particle P from the fixed point O. D would be r sine theta. So this would be like mv into r sine theta. Perpendicular distance of the line of action of the velocity from the fixed point O would be the angular momentum. Of course, there is a world of things that you would have to know about angular momentum, but then again, a basic understanding. The other thing now, if the particle is being acted upon by a force F, if the particle experiences a force F whose line of action passes through this fixed point O, if this particle P experiences a force F whose line of action always passes through O, this fixed point O, then the torque that F produces about O will be 0. Then the torque produced about O of F is going to be 0, right? Because what is torque? Torque is perpendicular distance of this line of action from the fixed point O, which is 0. So the torque about O is going to be 0. Torque about O is going to be 0 in this case. If the line of action of the force passes through O, it's going to produce no net torque about O. And once this happens, if at all times the particle is being acted upon by a force whose line of action always passes through the fixed point O, then the torque at every instant acting on the particle about O is going to be 0. And when the torque about O is 0, then the angular momentum of the particle remains conserved all the time. That means if torque about O is 0, then what we will learn down the line is that the angular momentum of the particle L, which is angular momentum about O will be a constant. It will maintain a constant angular momentum about O. It will maintain a constant angular momentum about O. Right? We can also show that if the particle P moves in a manner that its angular velocity about O is omega. If the angular velocity of the particle about O, you don't have to necessarily have an angular velocity in circular motion. You can have omega in general. If you would have seen my classes, first class on rotational dynamics, then you would know that omega can be really general, right? So if the particle has an angular speed omega about O, then its angular momentum about O will always be its moment of inertia about O into omega. That would be its angular momentum. I times omega would be its angular momentum about O, which would be the same as mvd. At any given point, that would be the same as mvd. If the moment of inertia, which is mr squared for a point particle, into omega at that point, that will be a measure of, that will measure the angular momentum of the particle about O. In the absence of any net torque about O, the total angular momentum of the particle about O will remain preserved or conserved. That's the law of conservation of angular momentum, right? So now, with this background in place, we'll quickly look at downright basics of elliptic motion of particles or bodies around a fixed gravitating mass, right? Suppose a body is describing an elliptic path. About a mass m placed at some point O, about a mass m, gravitating mass capital M. Under the influence of this mass m, suppose a particle describes an elliptic path. The particle describes an elliptic path. A particle of mass m describes an elliptic path. Then this is the point which is closest to the gravitating mass, and this point is called the perigee. This point which is the closest, this point A which is the closest to this point is called the perigee, where this M is placed at one of the foci. About M means this point M would be one of the foci of the ellipse. This M would be one of the foci of the ellipse. So if there is a mass executing an ellipse with another gravitating mass at one of the foci, then in its elliptic journey, there is a point A which is closest to M, and that point is called the perigee. And there is a point B which is farthest from M, and that's called the apogee. That point is called the apogee. The point O is one of the foci of the ellipse. Now, one thing for sure, while this mass small m executes an elliptic path, about a fixed mass capital M, that is under the gravitating influence of this fixed mass capital M, then at any point P, it experiences a force whose line of action will always pass through capital M. Whose line of action will always pass through capital M, is one of the foci, right? That's Newton's law of gravitation, right? Which means if the line of action always passes through the location of capital M, that means the torque acting on small m about capital M must always be 0. That means at any point the angular momentum about m must be conserved. Angular momentum about m must be conserved. Clear? Now, once we understand this, let's say this is an elliptic path described by a particle given as x squared by a squared plus y squared by b squared equal to 1 with another gravitating mass capital M at one of the foci. Then, let's say at a given instant the particle of mass m is at p, at a distance small r from capital M, one of the foci, at a distance small r from one of the foci, that is capital M. After a small time, that is, this is at an instant of time t, right? After a small time dt, let's say the particle arrives at p prime, in a small time dt. Then this r remains practically the same, in this small distance. This mp and mp prime are roughly the same in the small time dt. And let's say it describes a small angle d theta at the focus. It describes an angle d theta at the focus while describing this path pp prime. Now, for a small d theta, this pp prime is as good as an arc of a circle, This is practically like a circular path for a small time dt. This could be approximated to be a circular arc, right? With this being r, because r remains practically the same, it's almost like a circular arc centered at m in a small time dt in its journey from p to p prime. Describing an angle d theta at the focus. Now, since it's describing an angle d theta in time dt, very clearly, its angular speed over pp prime, would be like a d theta dt. Its angular speed over pp prime is going to be d theta by dt, that is d theta dt is going to be its angular speed, and its angular momentum is going to be I times omega, its angular momentum about m, its angular momentum about m is going to be moment of inertia about m, which is mr squared. Mr squared would be its moment of inertia about m, right? Into omega. That's going to be angular momentum about m, yes or no? I times omega. Where? So this remains constant. So while the particle describes this elliptic path, at different points r would be different, omega will be different, but mr squared into omega will remain constant. The distance from the focus m will be different at different times, omega will be different at different instants, but mr squared omega will be a constant commensurate with the law of conservation of angular momentum about m, one of the gravitating masses which is placed at the focus of the ellipse. Clear? So this will remain constant at all times. Omega is like a d theta dt. So we have r squared d theta dt equal to L by m, which is a constant. L is a constant. Angular momentum is constant at all points of this elliptic path, right? L by m, r squared omega is L by m, which would be a constant. L is the constant angular momentum that it has at all instants, right? M is the mass, and omega is written as d theta dt. Clear? Now, in its journey from P to P prime, about the focus where the mass capital M is placed. This is the sector area that it describes. This is the sector area that it describes. This is the area dA described in time dt. This is the area dA described in time dt, right? And very clearly, this area of enclosed by an arc, this area enclosed by an arc is half of r squared d theta. Do you know this? Is half r squared d theta? Half r squared into the angle at the center, that's the area. If d theta is in radians, then half of square of the radius into d theta, that's the area at the center. The length of the arc would be r d theta. The length of the arc would be r d theta. This area is going to be half r squared d theta, right? That means the r squared d theta is like a 2 times dA is like a 2 times dA. So this r squared d theta could be written as 2 times dA, right? So we have 2 times dA dt. This is small m, by the way. This is L by small m. This is small m. 2 times dA dt is L by small m, where dA dt is the rate at which area is described about the focus m. dA dt is the rate at which area is covered about the focus m. dA dt is the rate of description of the area. Rate of description of the area. So that means dA dt, the rate at which area is described about one of the foci, is L by 2m, which is a constant, right? That means equal areas are described in equal intervals of time. Equal areas are described in equal intervals of time. Do you understand this? That's the law of areas. Equal areas must be described in equal intervals of time. This is the law of areas. Equal areas described in equal intervals of time. Which means if, let's say, this is the gravitating mass m causing a particle, causing another body to describe an ellipse with this at the focus, then the area described in 5 seconds about m from this point to this would be the same as the area that it would describe in 5 seconds anywhere else. If you take 5 seconds from here to here, or you take 5 seconds from here to here, the area described about m will be the same. That's the law of areas. That's the law of equal areas described about m in equal intervals of time. And this m could jolly well be the sun, and this could jolly well be the earth. The earth accommodating an elliptic profile, accommodating an elliptic path with sun as one of the foci, will describe equal areas in equal intervals of time about the sun, right? So it's not necessarily the earth and the sun. For any particle describing an elliptic path about a gravitating mass as one of the foci will enjoy this law of areas. Equal areas described in equal intervals of time. Got me, right? Are you there with me on this? And the rate of description of the area is going to be the angular momentum, constant angular momentum that it has at any point, divided by twice the mass of the particle. Clear? Let's say the gravitating mass m at one of the foci, and these are the extremities of the major axis of the path described. This is the center O, with OA and OB being equal to A, the semi-major axis of the elliptic path, and OM being A times the eccentricity of the ellipse with OM. M is one of the foci, O is the center of the ellipse, right? The midpoint of the major axis or midpoint of the minor axis, that's the center of the ellipse. And OM, like I said, would be AE. The coordinates of M was minus AE0, so OM would be of length AE. E is the eccentricity. Now, at the point A, which is the perigee, it will have a velocity v1, which would be perpendicular to the major axis, because perpendicular to the major axis at this point will be the tangent to the ellipse. The velocity will always be along the tangent. At any given point, the tangent to the path will describe the direction of the velocity at that point. v1 is the velocity at this point for a mass small m at the perigee. At the apogee, v2 is the velocity. v2 is the velocity at the apogee. Now, AM, let's say, is R1. AM is R1, which is very clearly, this is A, and this length is AE. So, AM would be A minus AE. R1 would be A minus AE. That's R1, which is AM, right? Now, the distance of the apogee from this focus. Now, this length is A and this length is AE. So, we refer to this BM. We refer to this BM as R2. This BM is referred to as R2. This is R1 and this is R2. Very clearly, R2 would be A plus AE. Distance of apogee from the focus gravitating mass capital M is going to be A plus AE. And very clearly, R1 plus R2 would be the major axis 2A of the ellipse, which you can see by adding the two. Now, since this mass M is moving solely under the gravitating influence of capital M, which is producing a conservative force field, so the total energy of the mass small m in this field, kinetic plus potential, must remain preserved, right? At A, the kinetic energy is half m v1 square. And it's at a distance r1 from capital M. So its potential energy at this point is going to be minus G capital M small m by r1. That's going to be the potential energy at A, minus capital G capital M small m by r1. That's the potential energy at A, right? So minus G mm by r1. That's the total mechanical energy at A, which in turn must be equal to the total mechanical energy at B. The total mechanical energy at B is half m v2 squared minus g mm by r2, right? Half m v2 squared is the kinetic energy, and this distance is r2, so the potential energy is minus g capital M small m by r2. R2 is this length, right? So that's the law of conservation of energy applied between perigee and apogee, right? Then the other applicable principle is going to be between A and B, the total angular momentum is conserved. The total angular momentum is conserved. The angular momentum L at A is going to be mv1 into r1. See, this is the line of action of the velocity, and r1 is the perpendicular distance of the line of action of the velocity from M, right? So small m v1 into r1 is the angular momentum about capital M at A, and which in turn must be the angular momentum at B about M, which is going to be mv2 into r2, mv2 into r2. right? Now, very clearly, you can solve these two equations for V1 and V2, the velocities at the apogee and perigee, in terms of R1 and R2, right? Use this equation and use this equation. And V1 and V2 could be solved for in terms of R1 and R2, right? Or what you could do is, the other thing that could be done is the following. This V1 could be written as L by MR1. This V2 could be written as L by MR2. And V1 and V2 could be plugged in as L by MR1 and L by MR2. So you can solve for L, the angular momentum, in terms of R1 and R2, yes or no? You can solve for the angular momentum L in terms of R1 and R2, clear? Okay, once you know L in terms of R1 and R2, which in turn are like a minus AE and a plus AE, which means L can be known in terms of A and E. If they are known in if L is known in terms of R1 and R2, that means it's known in terms of A and E, the semi-major axis and the eccentricity of the ellipse, right? So essentially, I can solve for AL in terms of small a and E. Are you all convinced about this? I can solve for capital L, the angular momentum, in terms of small a and E. Once I do that, then realize that the rate at which area is described about M is L by 2M. We figured that out, the law of areas. Constant description of rate of description of area about the focus, capital M, dA dt is L by 2M. This we know. Now L is known, so dA dt is known in terms of A and E. dA dt will be known in terms of A and E. Now once dA dt is known in terms of A and E, then one result again which I have to tell you is, if this is an ellipse with semi-major axis A and semi-minor axis B, then the area of the ellipse we learned will be pi AB. If you put B equal to A, you will get the area of the circle, right? Pi r squared. If B is A equal to R, you will get the area of the circle, pi r squared. For an ellipse, it can be established using integration that the area of the ellipse is pi AB. A is the semi-major axis and B is the semi-minor axis, right? Where B is known in terms of A. Why? Like I said, B squared is A squared into 1 minus E squared. So B is like a root 1 minus E squared. So B is also known in terms of A. So the entire area of the ellipse will be known in terms of A and E. The area also known in terms of A and, so we know the entire area in terms of A and E, the complete area of the ellipse. And we know dA dt, rate at which area is described, L by 2M, also in terms of small a and small e, right? Now, the time it takes to come back to the same spot on the ellipse, that's the time period of revolution. If it starts here, goes back and comes back to this point, then that's the time period of revolution. That's the time period of revolution, yes or no? That's the time period for Earth. It's 365 days around the sun, right? That time period, very clearly, if you have to compute that time period, then that must be, in this time t, how much area is described at M? The complete area of the ellipse. How much area is described at M in this time t? The complete area of the ellipse, which should be pi AB. And this is done at what rate? How many square meters per second? At the rate L by 2M square meters per second. So this area described at the rate L by 2M. So this would be the time. This is the total area, meter squared, and this is meter squared per second. So this would give you the time in second to describe a full area. That means to cover a full revolution, to come back to the same spot on the ellipse. So this is the time period of revolution, right? This is the time period of revolution. B known in terms of A, so this is known in terms of A, this is known in terms of A and B, and so on and so forth, right? Once you plug in everything, what you would get, the final result, which is most important, is that G you'll get proportional to a to the power 3 by 2, where a is the semi-major axis. Eventually, when you plug in everything, you'll get the time period t proportional to a to the power 3 by 2, where a is the semi-major axis of the ellipse described. A is the semi-major axis of the ellipse described. That means square of the time period will be proportional to the cube of the semi-major axis. Square of the time period of revolution will be proportional to the cube of the semi-major axis. And that's the law of the time period. Square of the time period proportional to the cube of the semi-major axis. For a circle, the semi-major axis is the same as the radius of the ellipse. So then, in principle, 1, if this is the sun, this is the planet, then the planet will describe an elliptic path with the sun as one of the foci. 2, the earth or any other planet will describe equal areas and equal intervals of time about the sun. 3, the square of the time period of revolution will be proportional to the cube of the semi-major axis. And this sums up Kepler's laws. This is Kepler's law. Not just true for the earth and the sun, but for any other particle describing an elliptic path with a gravitating mass at one of the foci, these laws will hold good. Right? In principle, the law of conservation of angular momentum, that was fundamental, and the law of conservation of energy. These were two essential attributes to arrive at all these laws. Got me? This is Kepler's laws. This is all. You've understood everything about Kepler's laws? The law of areas, the fact that sun is at one of the foci and an elliptic path is described, and then the square of the time period of revolution proportional to the cube of the semi-major axis. So, no confusion, no qualms, no issues. Now, although my digression in the last 2 sessions, including this, on gravitation is enough for your school, but by no means is it complete or authentic or sanguine. And again, at this point of time, when your school exams are hovering over you and you have mental fears of varied nature, I didn't want to impose something very authentic on you, because that would have added to some anxieties. Yet at the same time, I do want to communicate the true spirit of gravitation to you, for which I will pass on, not today, but maybe after your school exam, I'll pass on the true spirit on gravitation in the form of a DVD to you, which you can see, and you would realize that, well, that was gravitation. And in that, I don't even talk about variation of G with height, depth, color, aroma, smell, etc. Right? But then it would be important once the pressure on you from school exams is shed, you'll be better geared to assimilate true gravitation, right? But for the timing, even for an IIT JEE kind of an exam, the principles that I have enumerated, this will suffice. This will suffice. Whatever I have said to you would be enough. I might have to add a few niceties here and there, which would take place during our digressions on problem solving. But there are issues again, which are more about electrostats, and which I would have those issues inherited to gravitation down the line. So I don't want to give a multiple treatment to the same issue. We'll have that issue dealt with in electrostats, and then I'll suggest to you that, well, the same results can be inherited in gravitation, because the force fields, the character of the force fields, gravitation and electrostatics is the same, save the fact that in electrostats we'll have forces both attractive and repulsive, because nature would present charges of 2 kinds, whereas since mass is only of 1 kind, forces between masses would be unique. They would always be attractive. So it would be a subset of our digressions on electrostats. So there would be issues which I would refer to as self energy and interaction energy, and we would have those issues taken care of in electrostats, and we can replicate the same formulas, the same result, replacing the masses by charges by mass, and we will not have to reinvent the wheel for gravitation then. So I have kept you away from those issues right now because it will be duplication of effort if I discuss them now as well as in electrostats. So we'll reserve those discussions in electrostats, and at that moment I'll tell you that, well, the corresponding result in gravitation is just this: replace the charges by masses. That's all. So we're doing all right here, and like I said, I will keep the next week suspended in as far as classes, formal classes are concerned.